What you are viewing is an example of valve trim damaged by a phenomenon known as cavitation. In addition to its destructive capabilities, cavitation can also result in unacceptable levels of noise and vibration. It can also limit the maximum flow through the valve. In a few moments, you will have the opportunity to see and hear cavitation resulting from water flowing through a control valve. But first, let's take a few moments to just examine what cavitation is and why it occurs. Cavitation is simply phase changes of a liquid. The fluid changes from the liquid phase to the vapor phase and then back to the liquid phase again. These phase changes occur as a result of the pressure changes occurring as the water passes through the control valve. Consider a simple restriction such as an orifice plate in a pipe. Liquid passes through the restriction. Various forms of energy are exchanged in such a way that the mean pressure of the liquid decreases to some minimum value. This is usually referred to as the vena contracta pressure. As the fluid moves into the downstream pipe section, the pressure again increases, but is not fully restored to the value it had at the inlet. This is because some of the energy was irreversibly lost through fluid friction. The key pressure is the vena contracta pressure. As long as this pressure is sufficiently high, the flow is free of cavitation. If, however, this pressure should drop below the vapor pressure of the liquid, it becomes thermodynamically unstable and partially vaporizes. If, on pressure recovery, the local pressure rises above the vapor pressure, the vapor is again thermodynamically unstable and rapidly reverts to a liquid. This is the cavitation process. Should the local pressure not recover sufficiently from the vena contracta pressure, but rather remain below the vapor pressure, the fluid will remain a vapor. This condition is known as flashing as opposed to cavitation. A special valve installation has been prepared to allow us to actually see the cavitation occurring downstream of a control valve. Let me point out the main features to you. A 2-inch Design U ball valve has been installed in a 4-inch Schedule 40 pipe. The ball is traveled at about 2/3 open and has been installed in the reverse position to afford a better view of the cavitation. The inlet pressure will be monitored by a computer at this position in the 4-inch pipe and is displayed on the computer screen during the demonstration. Immediately downstream of the valve, a flange with a pressure tap has been installed. This position nearly coincides with the vena contracta position and will give a good indication of the minimum pressure in the flow stream. This pressure will be displayed alongside the inlet pressure so that we may compare the two values. The downstream pipe section is made of transparent plastic to enable us to see the flow stream, since it is in this region that vapor and cavity collapse take place. Under normal flowing conditions, that is, no cavitation, the water will appear yellow in color as a result of the rust inhibitor additive. This does not affect cavitation, but in addition to protecting the system, makes the water more apparent. Cavitation will appear as a frothy mixture of liquid and vapor in this region. Finally, the downstream pressure will be measured at this location and displayed on the computer screen along with the other pressures. Now let's take a look at the actual laboratory installation. We have the ball valve, the vena contracta pressure tab, and the downstream viewing section. During the demonstration, inlet pressures of 100 pounds per square inch gauge, 150 psig, and 200 psig will be maintained. I will control the back pressure on the test section and consequently the pressure differential across the test section with this downstream control valve. There are 4 things to watch for as the demonstration proceeds. First, notice the noise. This will probably be the first indication that cavitation is occurring. Cavitation noise has been described as sounding like gravel rattling around in the pipe, and many times is the only evidence that the liquid is cavitating. Second, notice the vena contracta pressure. The laboratory test water has a vapor pressure of approximately 0.4 psi-A. Relative to our local atmospheric pressure, then, this results in a substantial vacuum between the environment and the vena contracta pressure. Also notice the large pressure drop taken from inlet to the vena contracta and the relatively short distance over which it occurs. Third, take note of the physical location of cavity collapse. This is the critical region, since this is the region in which the noise and vibrations are generated and the region most likely to experience cavitation damage. You'll notice that it is a function of the back pressure on the test system and will move upstream and downstream according to changes in the back pressure. Finally, notice the cavitation intensity and how it changes with service conditions. Let's begin.
The three key pressures will be displayed in the lower right-hand corner of the screen during the demonstration. We're currently holding approximately a 35 psi drop across the valve and find no evidence of cavitation. However, as we increase the pressure drop to approximately 75 to 80 psi-D, a moderate level of cavitation exists. Notice the frothy appearance of the water just downstream of the valve. The sound pressure level under these conditions is approximately 100 dBA. As I decrease the back pressure, the cavitation extends further downstream. Under these flow conditions, a strong vacuum exists at the vena contracta. This is evidenced by the indicated value of pressure as well as the suction present at the tap when I open this small valve to atmosphere. Notice as the inlet pressure is increased from 100 to 150 psi-G and then to 200 psi-G that an increase in the level of noise and vibration is experienced. Under these flow conditions, the sound pressure level is about 108 dBA. Again, if I remove the back pressure, the fluid remains a mixture of vapor and liquid through the test section. We've again imposed a 70 to 80 psi-D pressure differential across the valve. However, at this higher inlet pressure of 200 psi-G, cavitation does not occur.
Now that we've had the opportunity to see and to hear actual cavitation, let's take a closer look at a valve part actually damaged by cavitation. Cavitation damage is caused by high-velocity microjets and shock waves which are set up when the cavities collapse. In order to be effective in producing damage, these cavities must collapse very close to the surface. This results in a very rough, pitted, cinder-like surface. Another type of damage which on occasion occurs in a control valve is that due to erosion. Erosion damage is typically very smooth and very polished, a stark contrast to the rough, cinder-like cavitation damage. The final issue, and perhaps the most important issue, is how to control cavitation damage. Unfortunately, there is no simple, single answer to this question. There are a variety of methods and approaches to solving the problem. These can be grouped generally into three broad categories. 1, system design. 2, material selection. And 3, cavitation control products. The most preferred approach is that of system design. We saw an example of this during the demonstration. We imposed an 80-pound differential across the test section with an inlet pressure of 100 pounds per square inch gauge. Under these conditions, there was a moderate level of cavitation in the downstream pipe section. When we imposed the same pressure differential and hence the same flow rate through the valve at the higher inlet pressure, there was no evidence of cavitation. We've seen that cavitation is a liquid phenomenon that's associated with phase changes and liquid pressure changes. Cavitation can produce unwanted noise, vibration, and material damage. It's a function of the service conditions, and understanding of these can help in controlling and effectively eliminating cavitation and its attendant side effects.